get the Babcock and Wilcox perspective of mPower. Jack has 31 years of commercial nuclear experience. He also had been a prior officer with the Navy. For the past 13 months, worked with Generation mPower supporting project and business development, and now is responsible for the North American development. So, Jack.
All right, good afternoon. I get to touch off right after lunch instead of right before. That's always a challenge, but I think I'm up to it. Dan Stout was originally on the agenda, off the agenda, on again, off again. So I had to put together a presentation that potentially covered the TVA piece I needed to. And then he showed up, so the good news is he's covered a lot of what I might have, a lot more than I might have. After all, Dan made some great points, and I always like to touch off, maybe emphasize some of those. I will say first, though, I spent 15 years at TVA. That's not too long. It's certainly short enough to make a contribution and understand fully that issue that was raised about TVA being a federal agency that's looks like a private company potentially. But it wasn't too long to become stale. Although I will say, when I started with TVA, my hair was the color of Dan's. So maybe I would stay a little longer than I should have in the end. I have been working with B&W since last August, so for almost a year now. And I took over the North American Business Development Group when Ali Azad, who worked for them, left at the end of July. So my focus is Canada, U.S., and Mexico. And there's just as much happening in each of those countries on SMRs, which is not a lot right now in terms of actual contract to build, with the exception of TVA. So that's why we talk a lot about TVA. They are our lead customer for our design worldwide, and we hope to make them successful. So when Dan gave you a lot of his opinions and strong points, we're hearing every one of those as we work with them. I will say, though, Dan certainly does put out that strength of the federal government part of TVA a lot, because he tells you what they're not going to do a lot of times. And so we have to keep encouraging him to come up with ways to figure out how we're going to overcome some of those barriers and problems. A good example is he said in his talk, this first one's going to be like a model home. But we're not going to build this unless somebody gives us more money. And we're not going to build it if we're the only one being built. So we got to see that 4, 5, 6, 7 of these things are being built, are going to be built at the same time. I said, I was going to say, well, Dan, why don't you just say, if you're going to open up a model home, you just charge for tours, and there comes the extra money you get. We just need him to get a little bit more creative on some of that. I will also, I think in Dan's talk, and the good thing about his talk is, as you notice, he talked about SMRs, and I think the question did get asked about other investors, but it was also, are you interested in maybe other technologies, and are you locked into doing just B&W? And I believe he does not say we're only going to do B&W, but they are in a relationship with us right now to where everything they're doing is tied to using our technology. But ultimately, the work they're actually doing at the Clinch River site, which is primarily environmental studies, and they're getting ready to do a NEPA evaluation of their own for the decision-making process that TVA has to go through. That could be applied, most of it, to any of the SMR technologies at the end of the day if they chose to go somewhere else. So again, we have to keep them happy and make this work. And so what I'll do in my talk is specifically go into a little bit more detail about B&W's SMR technology, where we are, how much we've done, and how much we still have left to do in a number of these areas to make this work. All right. Let me disclaimers in these packages, because we do have a contract with the Department of Energy, and so we're required to put it because some of the work is influenced by that relationship with them. To begin with, when you start talking about building reactors or contracting for reactors or even contracting for licensing of reactors, you really want to know that it's not just about technology. Technology is important, but for those that work at Oak Ridge and Y12, you know that there are lots of technologies that work and can do the job. It's often more about who can really deliver at the end of the day the technology that we're interested in. When we get to time to have contracts, who's going to, one, be able to do it on time or on budget, is always important, or at least near to it. And the second thing, of course, is after something's built, if it has to be supported, who's going to be there to support it? So a lot of the SMR technologies that we read about worldwide clearly are growing out of the R&D world within laboratories or universities, or they're a new idea for some companies, or a company itself is being formed around the idea itself of that technology. Those are all good things, but they're probably not the best way to get something to market and make sure that it works. So the question is, who is behind Generation mPower and what makes it work? And this first slide, which you've seen now for several minutes, really reemphasizes that point, which is Babcock and Wilcox was originally the conceiver of this idea, but they're not new to the nuclear commercialization game, and they're not new to even nuclear power support today. They have a long history, over 60 years of experience. They did work on the original submarines that came, that were nuclear submarines at the time. They did work on a couple of commercial ships that had nuclear power as their source of power. They then went into the commercial nuclear industry. Of course, they sold, a lot of you know from that history, they sold a lot of their nuclear technology and experience to other companies over time, but they never got out of the nuclear game. They always did the U.S. Navy, both fuel and both products, nuclear products. And then they decided to pick back up from that knowledge and skill and ability they had and create this new product of the SMR. I thought I had a slide in there on, well, probably the next one. Currently, today, just working on Generation mPower, they can leverage facilities, manufacturing and engineering facilities they have in North America, both Canada and the U.S. Cambridge, Ontario is the one in Canada. That's where they make steam generators and reactor vessel heads. They've been making replacement steam generators for the commercial nuclear industry they always kept that business when they sold their other portions of their commercial nuclear business, their services group, for a while. But in Euclid and Barberton, they do nuclear Navy manufacturing work. Frederick is on here because as part of Generation mPower, we'll see they are teamed up with Bechtel Power Corporation, also with over 60 years experience in the commercial nuclear world. And Lynchburg is where the B&W fuels and their engineering group for B&W is located primarily. And then Charlotte, North Carolina is now where B&W headquarters is and where the Generation mPower headquarters are for the folks that work directly for Generation mPower. As I said, they formed, after B&W actually launched this back in about 2008 timeframe, so they've been at it for a while. And then shortly thereafter, they found Bechtel to work with because they really were an NSSS designer and supplier and a manufacturer of nuclear-grade components. And the idea was to now find someone who's good at project management of large commercial work, nuclear work in particular, as well as being able to then contract and manage construction of these projects. So that's where Bechtel came into play. So they formed a consortium, really, or a group with them, and they called that Generation mPower. The words are thrown out freely and often without a lot of definition. People will still call this the mPower plant, even though it's really using the mPower designed integral reactor, which is the B&W NSSS piece. But the plant should be a Generation mPower plant because it's a combination of the Bechtel design and the Generation mPower design. But, like I said, the words get thrown around interchangeably, and don't lose track of that too much, now that you know the difference between them. The objective, of course, of this alliance between these two groups is to be able to design, license, and deploy the first commercial plants, which we're trying to do. Notice we say it's a Gen 3++. We'll talk about that in a moment because it's got a lot of the AP1000 features, which are Gen 3+, and we're trying to go even a little bit beyond that in terms of the safety standards that we're trying to do and how we're trying to go about it. A lot of factoring in the Fukushima lessons learned, making sure that those are all covered. But we also want to be able to expand not only into the U.S. market, but into the worldwide market and fill a niche that exists for small reactor size plants so that people can take advantage of nuclear. This being, a lot of folks have seen this. I think those that understand the designs, it's not really to scale, but it's an interesting way of conceiving it. This is part of the issue of economy of scale, how a small reactor might be competitive with large. You take all these individual large components that make up existing large reactors, and you basically consolidate them all into the single integral reactor that's on the right side of the screen. And so that inside, we got those little reactor coolant pumps on top in our particular design, but they're part of the reactor pressure vessel boundary, the way that they're designed into it. You got the steam generators that are internal on top of the fuel. You got the pressurizer that's internal. So essentially, you've got a single integral reactor that replaces all these individual components. And the components themselves tend to be smaller, although small is a relative term. This integral reactor on the right-hand side is over 80 feet tall, so it's not like it's real small. But the other part that makes small reactors, and even large reactors to a certain extent, hopefully more cost competitive, is the ability to modularize much larger portions of the plant. The goal, Dan had this slide in his, he didn't talk about it too much, but the goal is to have 70% of the design of generation mPower modularized. Maybe not completely for the first of a kind, because as Dan said, we may have to learn some things from the first of a kind before we can lock in on the most efficient ways of doing it. It means that large portions of these modules will be made in factories and shipped to the site. So everything's being designed to go on rail or large truck. You can use barge, you can usually do larger stuff, but the idea is to be able to get it there on a truck if you need to. But you don't also always have to build a factory. You can build a local fabrication facility on site, which they're doing for the large reactors, to take smaller modules that might be shipped there and pre-assemble them there on site in a controlled environment so that they're not critical path for when you go to build the actual reactor itself. When we first started conceiving the generation mPower or the B&W mPower design, how big do you make it? And of course, one of those constraints that we thought about was this issue of what's the largest output we can make and still ship it on a truck or on rail, because that's what the concept was. We had to be able to do that. We originally thought the largest we could do was about 125 to 150, and we were in that range. As we got more efficient on doing the fuel design and the reactor design and understanding the details of what we were working on, we've eventually been able to upgrade it to 180 megawatts per unit, which is what Dan mentioned. And those 180 megawatts, though are configured, we think is the most efficient way to do it is to configure it in two units built side by side and not sharing any equipment. So they're standalone units, and with the exception of taking some efficiencies on the actual reactor building design itself, and the spent fuel pool can be shared between units. But other than that, there's very little sharing of systems between them, so you don't have to assume that the loss of a piece of equipment on one unit will affect the operation of a second. We do have large reactors bigger than that we know that some people are eventually going to want, and that's fine. If you're a big utility and your load is growing sufficiently to build large reactors in chunks, that's a good fit potentially. We do think that the cost that we are designing the mPower to compete against are comparable to a large reactor, especially when you factor in all the risk associated with large versus the smaller reactor that we'll be building. And therefore, we got this niche that's in this 360 megawatt range that will fit a lot of utility size applications. It's probably too big for some military applications, because people talk about small modular reactors being that. So I don't think any one SMR or reactor can be all things to all people. On the other hand, we think this one fits a pretty broad market, both nationally and internationally, that will allow us to gain considerable market share. Dan did talk a little bit about what his drivers were from an SMR point of view. And the good news is when we say what are we designing this to be and what do we think an SMR should be, most of those things are the things he found attractive. And that's one of the reasons why TVA has been working with us closely to try to promote this design. The one that came up after we saw what happened with large reactors, back when I was at TVA, we were looking at large reactors too. There was never a reactor we didn't think was interesting to look at, right? But we actually are building and finishing some of them too, including our older reactors as well as new ones. And when the AP1000 first came up, it was, when we were first looking at it, it was around $1,700 a kW back in around 2006 time frame, $2006. So, I mean, that was very attractive. People thought for new reactors it was going to gain a lot of momentum. And the market, of course, was much more robust at that time in terms of this. It was actually more competitive than other technologies, including gas, when we were first looking at it back in those days. Well, by the time the AP1000 finally got contracted for and built, it had doubled in price. And now the problem with large reactors, they can say it's only $4,500 a kW. But if there's 1,600 megawatts, that's a lot of cash, is the problem. And so an SMR may still also be 5,000. It may be even higher than a large reactor slightly. But when you look at how much cash do you have to take out of your pocket to build it a chunk at a time, it's much less than a large reactor. So the affordability, financeability piece of that is, one, how much do you really have to put up at a time to get some incremental amount of nuclear generation added to your portfolio? So that's become a bigger issue for a lot of utilities. Some people use terminology such as balance sheets of most utilities aren't large enough to put $12 billion on them for a single plant, which is what it might take to build a twin-unit AP1000 project. But they can put down $2 billion at a time or $3 billion at a time for an SMR. And then when that one gets built and starts making money for you, you can add another chunk. So you're always rolling that investment forward as you go forward. It is clean. That in the early days of nuclear competitiveness, people knew that was a value, but it really wasn't valued, and we didn't expect it to get value. Today, we do expect it to get value because they give value for clean to other technologies. The renewables clearly are in that category, and there's no reason why nuclear shouldn't be, because it does it more reliably and better than some of the other technologies which aren't being promoted. So that's still a hole for us in terms of how do we close that and allow a way for companies that are going to invest in this technology to be able to monetize the value that is being provided to the customers or to the nation for that particular attribute. Okay. The rest of these are self-explanatory. So domestically we have drivers, but internationally we also have drivers, and you would expect them to have some of the same drivers internationally, but you got some different ones. It turns out that not everybody has $3 natural gas prices right now with lots of combined cycles supplying the power on their grid. And there are places, believe it or not, around the world where electricity prices are high enough to build a nuclear plant and for it to be competitive. There's also areas where it's not just about the reactor and the generation source, it's about how do I transmit the power from wherever I build it, because there's not a lot of transmission capability. So you don't want to be pushing 1,500 megawatts to different locations. You might want to push 350 megawatts. So folks want nuclear in their portfolios. They want them in the United States too. It's not new here. A lot of the utilities that would want them in the U.S., though, already have a nuclear mix. So they're not starting from zero. There are a few starting from zero in the U.S. And the question is, when can they start kicking in to balance their portfolios more? And it will happen, but it's going to take a little bit longer, I think, in this country than it does in some of the places overseas. At least that's our current thinking. We're going to be in a position to move as fast as the market and the people want us to supply, though, in either nationally or international markets. All right, so where are we now? Well, part of the problem is, let's say the market was ready to that today, and gas prices were $10 a million BTUs, and we were competitive, and people said, I want a reactor, let's contract for it. Well, we're not ready yet. Our earliest we're going to be able to deploy this thing is if we had to be very aggressive, 2020 could be an aggressive goal. but it's more likely 2021, which is the current schedule that the TVA Clinch River project is on. And that's why I say they're our lead customer with our lead schedule to try to make all this come together. We do think that by the time this plant is in service, and certainly within a few years after it's in service, it will be a competitive form of energy with others. And the nice thing about nuclear is if you can get those first years under your belt, it gets more and more competitive over time against technologies because, as everybody knows, over half the cost is fixed and doesn't increase over time, or doesn't have to. And the only thing that's increasing is the fuel and the O&M, which is a smaller chunk of the total cost. All right, we do want to use, these are constraints listed here on what we wanted to design to. They're important constraints because if you're going to license a reactor in this country today, you don't want to take a lot of new technology licensing risk if you expect to move fairly quickly to get into the market. So we always have from day one, how do we leverage what's already been reviewed and approved by the regulator as much as possible to make this happen. So that's why we say Gen 3 plus, trying to look at things that have already been reviewed and approved. We aren't trying to introduce liquid metal, cooled reactors, which some people do have out there in the SMR arena. We're not trying to do the high temperature gas reactors. Light water reactor, the only thing new about it is putting together all the components in an integral way. Beyond that, it's still light water reactor technology. We wanted to improve the safety. We wanted to make it easy to maintain, operate. We only refuel every 4 years, which Dan showed. And we did early on try to think of outside the box. How can we deploy these reactors in more places? So we always thought about an air-cooled option. Again, air-cooled doesn't make it any more economical or efficient than it already is. It makes it worse. So the market definitely needs to be more robust if you're going to introduce those. But when the market becomes close or there's higher cost regions in the U.S. that have water limitations, but they want nuclear to be part of their balanced portfolio, we'll have an option that allows them to do that through air cooling versus water cooling, which saves a lot on water usage. Dan showed this slide. I don't think I need to repeat too much of it. I'll repeat some things that are important. One thing about Babcock's and Wilcox designs, the once-through steam generators allow significant superheat of the secondary steam, which tends to allow for the secondary plant to be more efficient than some other light water reactor designs. So the 50-degree, superheat in the secondary loop common here is about that. We give up some of that by, reactor coolant pumps using some of the power or something else, but it doesn't give us a good start on a highly efficient design. And the 4-year refueling cycles is good for operations and maintenance, and it offsets and lowers those costs. But for you fuel designers in the audience, you don't always optimize your best core design on 4-year cycles. You can probably do it on 12-year cycles a little bit more efficiently. So in some ways, the fuel cost will be a little bit higher potentially, but you would offset that in O&M cost. All right. And the convenience of being able to operate for long periods of time without having to have those outages. The underground feature was there from day one. Everybody says, now that you know how much it costs to build them underground, do you wish you would have done it another way? Well, we don't know what it would have cost to build them above ground with all the new requirements. It may have been just as much. And Bechtel has done a lot of work on optimizing how would they build it underground and do it in a way that doesn't add too much additional cost. This oval design that you see on the periphery of each of the ends here was a way to minimize the amount of concrete while allowing the same strength to the overall design. But the bottom line is the top of that containment building itself with the tank of water on top of it is below ground. All that's below ground or at ground level at the maximum. So that'll let you know what it's like with two of them side by side there. All right, then from the NSSS side though, what about the rest of the design? What did we have to take into account? Well, this gets back into from day one. We tried to inform the design with what we knew we were going to have to attack and improve upon if we were going to make this small size work. One of those was security, as we talked about. This was after September 11th when all this is happening, so we knew those requirements are out there. And we have to meet the design basis threat and all those requirements as it is. So Dan mentioned we could design certain features into any plant being constructed, and that was true. The other designs that are being designed today too can do the same thing. So we kept having the problem about, well, when you start putting a bunch of buildings close together, it gives intruders more places to hide, so to speak. So you worry about that. So one of the things we thought about early on is, one, how do we minimize the number of employees that work for the company, access to the critical infrastructure that you're trying to protect, and how do we protect it from potential intruders the best? And one of the ways was to separate the turbine building from the reactor building, as shown on this picture, where the blue is the turbine building and the big rectangle in the middle is the dual unit reactor building. And so you've got a physical separation there with physical fence separation too. Only certain employees will be allowed access to the reactor building structure. The rest of them will be over the secondary plant side of the plant. And it limits the traffic that comes through the plant that has direct access into the reactor building structure. So our argument, and what we were discussing with the NRC, and we were putting together topical reports and having discussions with them, is here's how we propose doing this, what we think the staffing requirements would be to meet the requirements. Please review this and interact with us, and hopefully at the end of the day, we will come up with an improved security design that, again, meets all of the same requirements, but can do it with a few less people than what we have to staff large nuclear plants with. Okay? So that was one item. I talked about the one-on-one TG alignment, which was important. You don't want to have one unit trip affect another one. Although for post-Fukushima type analysis, we may have to assume more than one reactor is affected at a site. We know all those things are going on. We talked about small EPZ radius, and I'll get that in a minute. So this is just real quick. See, that's the owner protected area of the big fence, rather around everything that you're limiting access to. But that is the area that's protecting the reactor building itself with its dual barrier fences. So the idea there is you've got these multiple barriers in different locations with different access and different trucks and stuff can come in, all the things happen. So that's a good point. Now, what about some other good points? How do we increase the safety margins if we can to the limit? What's the vision, or what are we trying to get to in terms of our design? These are not things that have been finalized yet. Dan said we're still doing design work. We're still having the NRC review the design work. So final numbers could change slightly. We're not trying to say these are the final ones, but there are goals. Our design goals are trying to get to these levels or better as we go forward. We do know that some of the brand new large Gen 3 plus reactors achieve 10 to the minus 7 to 10 to the minus 8 core damage frequency. So, but if you look at where is it compared to existing plants operating today, it's going to be an improvement over all of those and comparable to the best of the new ones that are being built on a larger scale too. We think, of course, it's small reactors, so there's not as many big penetrations. So we think deterministically we don't get a large break loco for this design. That's a regulatory issue that we have to have discussions on with the regulator, though. We've introduced some design features such as integral isolation valves that work almost like a check valve at the reactor vessel itself, even for the smaller penetrations, to where the break in a pipe doesn't lead to a loss of coolant from the reactor vessel. The question is, can we take credit for that or not? What testing is required? What pedigree is required for those kinds of things? So those we have topical reports and other presentations we're doing with the NRC that are trying to make the case that we don't have to assume a break at that location because of that, but we will. Stu, we can ask Stu that question. I don't know where it is when he's up here, but it's an ongoing conversation. Let's put it that way. Point is, though, there's lots of water above the reactor vessel where an actual break can occur, and we have a long time. The sequence of events, even with a break, because they're much smaller sized breaks that do occur, gives a lot of time for response of your systems, and we have passive systems initially to meet a lot of requirements. So, a lot of ways you work it. We think that the safety margins for this design are much improved over many of the other comparable LWR designs. All right, you can read the rest of it yourself. The last one, we talked about emergency zone. And Dan said the issue is not, do we just want to do away with the requirements? The issue is there's a basis for the current requirements to have to be implemented to protect the health and safety of the public due to an event at the plant. Can we demonstrate the same level or better level of safety, even if that protected area is moved closer to the plant site itself? And our goal here is to move all the way to the physical boundary of the site itself, or 1,000 feet is what we say. And I'll show you something on that in just a moment real quick. Or have a little bit more on it, say on it, I should say. All right, we mentioned how does this design compare to what would have happened if it were located in a Fukushima type environment. We know that we're designing it where it meets the latest seismic requirements at some of the worst locations in the U.S. Not all of them. It would meet about 85 to 90% of all U.S. locations. But one of the ones that is harder to meet is East Tennessee, because it has the East Tennessee seismic zone in this area that influences it. And as a result of designing it to umbrella that site, it's going to give us sufficient margin for a lot of other sites. But it's also going to be made watertight and protection against flooding events that occur from floods. The on-site power, we mentioned we're going to have passive safety systems where you don't reach a point where you run out and you go over the cliff edge and all of a sudden you're getting core melt and other things occur. Station blackout, we're going to have 72-hour batteries, we're going to have 14-day coping capability, which is a long time, and we can go beyond that with the flex type stuff the industry puts in place to probably address it. We may be able to go longer at the end of the day when we're done. Spent fuel pool can go 30 days without having to be made up to or any other additional features are added. So the point being is we have a good safety message. Small reactor doesn't need a large emergency zone because it's safe. And if an event were to occur, we have greater safety margins than other design plants that are out there today, or at least we think we do. And we said the problem today, it's not a problem, it's just a result of where we are today. You have a 10-mile emergency planning zone, which means you have to figure out how you're going to safely protect the community within that 10-mile zone. Makes it difficult to put a small modular reactor at a retired coal plant site that's next to a city, necessarily, because a lot of them were built in those kind of locations. However, if you can, this is the Clinch River site, which you can't tell from there, but if you can move it into 1,000 feet, you can easily put these at more sites and meet that requirement that you can for others. All right. Let me see where we are on design status, some highlights. Like I said, we're not starting the licensing only now. We're moving beyond, I'll talk about designing because that's feeding directly into licensing. But we're also going to be moving beyond, how do we get ready to construct a plant? How do we get ready to contract for a plant? What are we doing for making sure the operators can be trained on how the plant operates? All those things are already things we're working on and starting to put in place, even though we're not submitting the DCD until next year, and it will be a short 24 months before they approve. No, 36 months probably before we get it approved by the regulator. So we have a ways to go, but we're already beyond where we need to be to start some of those things. That's the point. That's the kind of effort you have to put in to be ready to build these plants when they're ready to go. And why you need to pick a company that has the ability to put those kind of things in place to have them ready in time. All right, full-scale development has been going on. We currently have over 500 FTEs. When you look at the entire B&W complex, that's supporting the design, manufacturing work, and other things on the SMRs. In Lynchburg alone, we have a couple hundred engineers, our staff, and in Frederick, Rebecca, we have a couple hundred more. So that's most of them. But we have them in Cambridge, Ontario, where they do the steam generator design work and things, reactor vessel design work from a manufacturing point of view, having to put procurement specs together, the other things that we have to do. Those kind of people are out there too. The fuel design and testing work is going on also. The NSSS is about 60% design complete. And again, you say, well, why isn't it 100% complete if there's so many design cert? Well, you don't have to be 100% design complete for that to take place. You have to have all the questions answered that you have to answer. But when we say design complete, we're talking about now going beyond just the conceptual design and the calculations, but starting to think about, like I said, procurement. What's the engineering and design requirements to build a reactor vessel and get it issued to the factory that has to do the building and things also. We do have all the nuclear island architecture defined now. We have not finished the seismic analysis. We had to get all those other pieces together to apply that on top of it. And it takes a lot of time to run those computer models to do that seismic analysis. But we're in that process now. We do have a full fidelity simulator that's up and running in Lynchburg already. I'll show you a picture of that in a minute. And like I said, the critical components, the steam generators, B&W Canada are designing those, and they're well along that path. Control rod design mechanisms being designed by in Ohio. They did a lot of work on CRDMs for the Navy, and so there's a lot of intellectual knowledge there. We started with an electrohydraulic. Remember, these CRDMs have to be inside the reactor vessel. So they're going to be in a high temperature environment and not on top of the vessel head like existing reactors. Clearly, the other designers are looking at the same thing. Westinghouse has their version of how they would do that. We started off with a concept that we thought was kind of slick, that was an electric hydraulic, where you'd lead off the pressure from the hydraulics dial that go into the core. It wasn't. We ran into some problems and some testing on that. We changed our design, and we're now starting to test the features of the new design. It's going more back to the electromechanical type designs that we've seen on other reactors. Reactor coolant pumps, we're using a can motor design, similar to what the Navy did. They're smaller. Of course, Westinghouse did that, converted them and have huge ones, 4 per plant. We have more on, and they're smaller. We think that's a slick design that we'll be able to put in place, and that design and testing is underway. And then the fuel design, we're already starting to do fabrication of components and other things, but we still got a lot of work to do on the fuel area. But as you can see, the critical heat flux testing is already 50% complete or beyond. And then we have this test facility in Virginia that was built. Again, these are not easy things to do and get in place. So when someone says, I've got this reactor design over here, and I'm going to get a license, I'm going to go put together a bunch of paperwork and submit it to the NRC. First question to ask them is, how are you doing all your testing? Because a lot of them aren't doing that. That's expensive to do, and it takes a lot of time to do it. Well, we have this facility, the tall chimney sort of looking thing in the middle it's to scale height-wise for the reactor, so that's why it's so tall, for the integral reactor, all the way to the steam generators and up to the pressurizer. But it's only about 1/32 to scale, circumferentially, so it can do scale testing. They built this thing several years ago, really started about a year ago doing the real testing, full temperature testing. It uses electric heaters, obviously, to get you up to the temperatures you need to do the type of testing, but it goes through all the testing shown on this screen, and they're well underway on that and doing that, collecting the data and information. So that can be used to validate our models and our predictions so that when NRC reviews what we say this design will do, we can show how the testing confirmed that it can actually do what we said. As I mentioned, the fuel is undergoing the the actual physical design. We do have facilities that have been doing fuel fabrication. This is the beauty of B&W and the infrastructure they bring to play. They have existing manufacturing facilities in place that they have managed for years that can do a lot of these pieces. And so how do we make all of them work together to make the mPower successful? And of course, change portions of it to be unique to what the SMR design requires. This is, you always see a picture of a couple of big TV screens and say, there's my simulator. Anybody can put that up, right? Well, the beauty is the software and the programs behind it that are simulating what the plant has to do, what the operator actually has to see, what he has to step through. The panel on the left would be, there's going to be an analog backup system to the digital processing system that we have. But this is now in place, and people are going through the testing and the validation, and at some point we'll actually have to go through the testing with operators through the final system, but that's a ways away still. This is where the control room design for the plant and how it will be laid out has been done. It's part of the physical part of the plant design. This is set up in a separate area now up in Lynchburg to just do the simulator validation and testing of the models themselves. Dan showed this slide. He did say we're doing Part 50 for Clinch River, and he talked about all the good reasons why. And he's correct. The problem is the new process that would work well for replication with the regulator and with others is the Part 52 single-step process, if you're not making lots of changes to the design afterwards. So we are working already with an industry team, and as part of our commitment under the DOE cost share program, to not only do the Part 50 licensing work with Clinch River, but to at least develop what we call a reference COLA template for the other process. And then hopefully we'll get a customer that steps up and wants to be the first of a kind to go through that reference COLA review with the NRC at some point. So we're going to have both, at the bottom line. If a customer really wanted to use Part 50 beyond TVA even, that's a choice they have under the current regulation. We think, though, that once it is standardized and built and licensed, the Part 52 process will be as good of an option, if not better, for them to follow going forward. So we want to position ourselves to have both available. Dan covered this, so I don't need to cover a lot more on it. He did mention $101 million. That's out of that $452 million DOE cost share program for 2 designs, which we were selected last year for and finally put into place this year. We have now been authorized $101 million out of that total pot. Obviously, if 2 was split in half, we'd get $226 million total over 5 years. So we're already to the $101 million level as of now. So we hope that continues to go forward and we get the full amount as part of this process. And Clinch River, that's not clear enough to tell you, but that's the 4 units or 2 twin packs that would be positioned on that site. Dan showed this, so I'm not going to repeat it. I think he made a strong message, and I agree with his message. We as a vendor have to try to develop this project assuming we don't get additional funding from the government. On the other hand, I've said in talks when I was back when I was with TVA even, there is no U.S. company, or actually there's no worldwide company that I know of, that has ever brought a new product to market without some form of government assistance or cost sharing with somebody along the way. And so can we be the first that ever does that? Not likely, and of course we already have a little bit of a cost share. Dan talked about DOE's plan to help the first movers move further by having maybe more investment in getting those first moving. That can be through the Department of Defense accomplishing some of its mission goals and figuring out how to pay what it's worth to them to do those things and just apply it towards an SMR potentially versus some other alternative way of meeting that same goal. And so we think there's a lot of room for discussion and hopefully a program there that doesn't have to do just SMRs, but SMRs can be a piece of that. So between DOE on some of their facilities or DOD on some of their facilities, we believe the critical infrastructure reliability approach is one worth more work and development. And the microgrids is the other part of that. I won't spend a lot of time on it. These are just terminologies that we use. Dan didn't have this slide, but it's common talk. There's a DOD conference coming up in Austin, Texas in November, I think. And they'll be talking about this topic among others while they're there. All right, so let me wrap up and open it up for questions from everybody. Progress overall towards deployment. We've got the cost share program, which is really doing a lot to keep us moving rapidly forward. The other thing that happens if you don't have cost share is you've got to balance. This is an R&D budget for B&W, as an example. So an R&D budget usually comes out of earnings from your other business lines that are making real money, right? So how much can you afford to spend on R&D at a given time? So if you don't have contracts, the money's coming in from the contracts, it's got to be fully, how much can I afford to take out of my operating profits to continue to spend on this? If you've got cost share with government, or you've got some other money coming in, you can do more, and that's what we're doing now. Because we've got money coming in from DOE, we're doing more, and we're doing it faster, and that will position us to commercialize this faster than we otherwise would. Detailed nuclear island work and major safety enhancements have been defined for us. We're locking that down and put together final technical reports and have interactions with the NRC on those requirements. We're already starting to prepare sections of our DCD. Many of them have been drafted already, so that's underway. We've got a testing facility. We've got a pre-licensing engagement ongoing on a regular basis with the NRC. The Fuel Technology Design Center is doing the fuel design, control room prototypes in operation, and Clinch River, as we saw, is done their site licensing work already. Not licensing, site environmental study work. They are preparing their NEPA evaluation work, and in parallel, they'll at some point do their environmental work to submit to the NRC under their, at the same time, or possibly slightly earlier than their CP. I don't know what their latest view on that is, but they could do that. They could do that separately in parallel path, or they'll probably wait till they get their NEPA answer before they submit it, which will be about the same time as they'll be submitting their design or the construction permit application. All right. There is a value proposition here, and that's what I'm going to close with. Reactors in this country today do not compete well with natural gas at $3. We know that. Gas won't be $3 forever, and portfolios are very electricity generation portfolios, or the people that have to have them, don't feel comfortable about all eggs in one basket. They never have. That's always been their philosophy over the years. So in the past, when you wanted diversity in your portfolio, you might have some slightly higher cost generation and some slightly lower cost generation in that portfolio to have that overall balance met. I think that's still true for nuclear. It may not be the cheapest alternative for a while. I think someday it will be again, but it may be a while before we see that. But as part of an overall portfolio, there's nothing wrong with putting a little bit of it in your portfolio that's a little bit higher cost. We do it with solar, we do it with wind, we do it with other technologies that we want to have part of that mix. We certainly can do it with nuclear. So, but in the meantime, we are trying to be as competitive with other technologies as we can, so that you're not paying much of a premium if you do on nuclear. And a good example is a $5,000 a kW overnight cost is comparable to what large reactors, or the ballpark of large reactors now. And when you factor that in over a 40 or 60-year life of these assets, it competes with almost every form of energy that we produce energy with today, except for natural gas at $3 WMBTs. But what happens when gas is $9 or $10? Well, guess what? Now we compete well with it too, or even better. All right, so the incremental investment is low and manageable. So from that point of view, you're not betting the company on your investment. And we think you end up with a safer, cleaner, more reliable product that is easier to operate, easier to maintain, and easier to regulate for the next phase of generation technology for nuclear. So that's who we are, and that's what we've got to offer, and I'll open up to questions. Yes?
Jack,
You can ask me TBA questions too, because I can say anything.
actually, that's what I was going to do. Actually, that's what I was going to do. Yeah, now that I listened to Dan's presentation and yours, and I kind of draw this Venn diagram. You know, we got the design going, we got the, you know, the power generation of TVA and their responsibilities. We have, you know, the NRC, you know, trying to work with it. But I kind of wonder that community piece of trying to convince the community. It's connected, I think, to Maurice's question early on. You know, what are we doing? Is there an obligation by Babcock and Wilcox and by TVA to, you know, to communicate this throughout the community, to get the buy-in, especially with Clinch River coming up, you know, and especially with sensitive communities like this area who, you know, the government just came and took and took and took. I mean, is there a responsibility? Did you want to comment on that part?
Yeah, I'd be happy to. A couple things to keep in mind. When we go in to try to market our product, wherever it is, whether it's in New Mexico or whether it's in Ohio or whether it's Tennessee, we try to find, because we don't want to, we're not the owner, we're not the electric utility company. We're the supplier of the technology. So we've got to find someone there that is going to be that utility company. and we need to have a partnership with them to try to make that happen. And we typically want them to be in the lead on interacting with their customers or their potential customers versus B&W doing all the talking for them. So you'll usually see us alongside them in those arenas versus on our own trying to promote it without them being. So that's why it was nice that TVA did make it today, for the discussion. The other thing in TVA's case in particular, remember they are getting ready to start on a NEPA process, which is a very public process that will engage not only the public in this community, but the public and around TVA's other communities too, to allow them to voice their opinions on this plant at this location and the impacts it might have on them or what they perceive those impacts to be. And there'll be public meetings held, interacting with those folks. So, that's, TVA does that, not everybody does that, which is important. We sometimes underestimate that because those of you that work in the government world, it can be a pain to go through the NEPA process publicly, but if you do it right, it accomplishes a lot of other things for you at the same time. The other thing is, every community that has a group, a community that represents it, whether it's E-Tech here in this community, whether it's the group that helps look at how do we convert parts of Oak Ridge into more productive facilities, whether it's just the local schools, UTK and stuff. We try to get out and speak and talk to them and have people available. So that's part of the marketing and business development side of B&W. And we invite people to come up to Lynchburg and do tours of the actual work being done up there and get more technical presentations or see the control room simulator or see that test facility and talk to. So we do outreach in a number of ways, and we try to leverage what works for the utilities in the areas that we're trying to talk to best. And then we have a legislative and government relations side of our house too that tries to make sure we're communicating with the right folks at the right levels there so they're not surprised by anything we're doing. But that's usually coordinated with the local utilities, so there's both of us doing it.
Just an anecdotal follow-up, you were joking with Dan, you could sell tickets, but we were actually talking about that. And on a serious note, that if you built the Clinch Riverside as a test site for the mPower, that you could probably, this is just anecdotal, you could do a little bit more public outreach first.
Right.
And that public outreach, here it is, you can bring folks there, more than educational element. But it was more, it was an independent thought that we had on the education side of UT. But you had it as a tongue-in-cheek, but I think it's possible.
But one of the thoughts we had earlier, again, when you're in a long-term development project, a lot of ideas come at a lot of different points in time, and it's always about when is the right time to start putting all the resources and energy into making this next thing happen, whatever it is. And so early on, we talked to UTC, University of Chattanooga, and about a centralized training facility. And because they did advanced modeling and simulation down there, would they be able to help us with our simulation, our simulator and simulation, and do things? And they were interested, but so the point is that was a reasonable idea. There's no reason why we would have talked to UTK about that too. We want to locate it up here, do we want to locate it down there? Where's the best place in the region to put something like that? Those are all good discussions, but at some point when you want to move to implementation, when's the right time to really do it, nail it down, and when do we just talk about it? So they're all difficult, and they all take a lot of effort for someone to do, and we just haven't gotten around to some of those things. Anybody else? Well, we just answered all Gary May's questions there too, right? I will put a plug in. We did use ORNL's Forsage software tool, which they developed to screen large portions of the United States, or all of the United States, to identify where are good places to locate SMRs or reactors or any other kind of plant, depending on what parameters you want to put on it. And it very quickly takes large geographic areas and tells you which ones meet your requirements or don't, whatever those criteria happen to be. So he'll talk to you maybe about that or other things, but we used it for some of our real work we're doing for one of our clients right now, and it actually helped quite a bit. So we try to take advantage of that kind of stuff here.
Thank you.
Thanks, Tom.